Let's get started. So hello everyone, I'm Jiarui and I'm going to present our latest work multimodal learning to improve cardiac lead mechanical activation from CMR images. And this work is done by our great collaborators from University of Virginia. And a quick spoiler before I dive into details. We talks about how to reconstruct image quick and fast and well, right? So our work is doing two things separately. First, if we have well reconstruct images, how do we track motion from them? Second, if we have motion and we know what disease we want to care about, in our case, the mechanical activation, how can we embed these things together? How do we make everything better? Okay, and here are details. So for some background, so cardiac motion, or especially cardiac stream, it has been proven to provide critical information for heart failure treatment. And cardiac magnetic resonance, or CMR image, is widely used, as we saw many cases examples today, because it offers high quality images for accurate string analysis. And here I have a visual pipeline of image collection, string analyze, diagnose, and finally treatment. And yeah, and in our research, we particularly focus on latent mechanical activation, or LMA detection. And what is LMA? What is latent mechanical activation? Well, so let's first look at the motion video from a healthy volunteer. We can observe that when it contracts, every location along the myocardial start contracting at the same time, simultaneously, right? That's a healthy person. And it can be even more easily identified from this video of circumferential string. You can see that here the blue means contraction, and you can see everywhere it turns in blue in the kind of same time, right? And here's a particular frame from the contracting start time, and you see all blue, or all contraction. But if you look at the motion video for image patient with LMA, you would observe that the lower right part, it kind of start contraction much later than other regions. And again, looking at the string, we can see the lower right part has much lighter blue or kind of greenish color, which means it indicates it's LMA region. And one example application of why do we care about LMA is that it has proven to be the ideal CRT leading pacing sites. In other words, if we place the CRT cardiac resynchronization therapy, electronic lead, and the LMA region, it can greatly improve the response rate. Okay, so we talk about motion, right? And the next question is, so the string is computed based on motion, but how do we get good motion, accurate motion? So the Cine and specifically Cine DSSP data are the most widely used CMR images, as mentioned before, because it has high quality and it's easy to access. It's routinely collected, and the most widely used approach for motion tracking is feature tracking, which works in an unsupervised manner than to try to find the motion and compensate the appearance changes between frames. And the initial feature tracking method is based on optimization, and there are following works to make the deep learning based variance, and there are also works to add the prior information or regularization. But the problem is that the appearance change in the middle part is just so minor that if you do it unsupervisedly and if you are driven by the appearance changes, you always get limited accuracy. You got kind of miss the motion inside the myocardium. On the other hand, I mentioned unsupervised, you can imagine. I'm going to supervised learning. So in contrast, we have this dense or displacement encoding via simulated echoes that directly gets, from the scan, we directly get motion, very accurate motion. And so this paves way for supervised learning approach, because now we have the ground truth motion data. And you may ask, so everybody just uses dense, right? Why do we care about this, how deep learning or kind of things? Why do I have this talk? It has accuracy, but the price is that it's very expensive. It needs expensive facilities, need to extended scanning time, and specialized knowledge for data collection and analysis. So here comes our research question. If it's possible to combine this to keep accessibility from Cine images, that can utilize DENSE to make an accurate motion prediction, and how does that works for our particular task, LMA detection? So based on this consideration, we propose the first work to leverage deep learning to improve LMA detection accuracy from Cine images, which means, for instance, only need Cine images and guided by highly accurate dense data only in the training time. Before diving into details, I need to go through a technical background of how do we represent the string and how do we represent the activation, how do we quantify that? And so if we have this video of myocardial strings along the different frames, and we can vectorize the string along myocardium into vector for each frame, and if we concatenate these vectors, we can have this beautiful string matrix where the x-axis shows time and y-axis shows location on the myocardium. And if we look at the early frames, we can see that the middle part shows yellow, which means it's stretching, and while in the same time, other part is showing shade blue, which is kind of you're contracting normally. And this means that middle part is LMA region, right? Because it's start contracting later. And we can, so how about activity time? We use this TOS, or time of onset of sequential shortening, to quantify the activation time. And if we kind of concatenately select the activity time for each of the location on the myocardium, along the myocardium, we can have such TOS curve. And visually, if we overlap the TOS curve with the string matrix, you can see it pass through the yellowish region. Okay, so now is the technical part. Our proposed approach, the joint multimodal deep learning detection. So it starts with a supervised motion detection module, which we get the input from CMR and predicts the string matrix, which represents the heart movements, with the guidance or supervision from dense accurate string matrix. After that, we would also include the element detection text to predict the TOS from the predict string matrix. And after that, even one more step, if we have this is done by on one slice, the previous steps. If we can collect the TOS time or activation time for each slice along of the same patient, we can build this 3D activity map that shows the activation time of different locations all along the myocardium. And in this particular image, you can see that the upper part is showing red, right? That means that the red part, the upper part has a long activation time, which means it's LMA region. And when you use CRT, you should put the actual meaning and then the location. Okay, so here are more technical details. So this is the full architecture. We have two parts: the reference guided string prediction network and LMA detection network. Let's focus on the first one. So the first one, it has two sub-networks. The first is the image registration module, which you can see that so kind of here we start not directly maps the images to some motion. We're kind of first it tracks using a supervised manner to track the non-perfect but imperfect but still very highly informative motion features from the network. So we can make an easy motion to motion transfer stuff to actually hardly transform motion to image to motion, and this is for enhance the whole robustness and accuracy of the whole network. And particularly we use unsupervised latent feature because it has lower dimensionality and can improve the efficiency. Also, it has richer information than we have the final LMA detection. And here's loss function, which is weighted on registration similarity, smoothness penalty, and modal weight decay. Next is the string estimation module, where we begin from the unsupervised latent motion feature and predict the string matrix, and with supervision of highly accurate dense data. And here the error is loss function is string prediction error and modal weight decay. And finally, we have, based on predict string, we can predict 2S and get 3D action time. And here it's just supervised learning, so the error is weighted on 2S estimation error and modal weight decay. And the whole module is learned in a joint learning manner, so we can optimize the string network at the same time with the total loss to be the weighted the sum of two and weights are included in each separate terms. So it's still the weighted sum. The weight is just not shown here. So okay, let's look at some experiment results. So for data, we use 118 slices from 24 subjects. So we see, okay, like 118 slices. So this is the problem why I say DENSE is expensive. It's even in trouble for us, and we're collecting a lot more data. Hopefully, it could make research more generalizable, and to improve the robustness of and performance of the registration model, we use binary Cine myocardial mask instead of the raw Cine images. But theoretically, you can use either. And we for the Cine sequence, we probably resize our Cine image to 120 by 120 by 20 frame volumes. And for dense string matrix, we land all the string matrix to 128 sectors by 40 frames. And we include 3 evaluation metrics. In first is LMA region classification accuracy, where for each location on the myocardium, we want to classify whether it's LMA region or not. And 2S regression, MSA, we directly estimate the 2S time, the activity time for each location of the myocardium, along the myocardium. And finally, we have the visual compilation of this 3D activity map relation. How well can we identify the LMA region if we just look at it and want to search for best CRT inside place. And for the input baselines, the first baseline is the retention model feature tracking algorithm. That's a widely popular used method. And second is the joint multimodal approach we have seen before. And we have a third reference method, which is LMA detection directly from dense ground truth or highly accurate stream images. Something like this. We do not use the predict stream, we use the ground truth stream. And this purpose is to evaluate the effectiveness of predict stream for the specifically for the LMA detection task. And we expect that the performance of our approach is much better than the baseline and should be close to the reference method. And let's look at the results. First, for 2S regression, here's an example of the feature tracking baseline experiment. And you can see that the black curve is ground truth and red curve is that curve is prediction, because it's quite large error, right? And for reference, you can see this makes, of course, if you use ground truth, it can make perfect prediction. And in the middle is our result. It's much better than the feature tracking and close to reference, right, as we expected. And yeah, and we have second case, and the conclusion still holds. And so that's it for some examples and look at the statistics. And again, our model is much better for LMA classification. Our model is much better than feature tracking, and not so close, but quite close to the reference. And same conclusion for the regression, much better than baseline. And for 3D activity map visualization here, right, and we are on the ground truth, you can see there's an region on the lower part, right? And for the prediction of reference in our method, it cannot capture that thing, right? It's not very accurate, but it captures. But for feature tracking, it just needs, if the doctors looking at this prediction, the doctor would just conclude that, okay, there's no LMA or very weak LMA, and the patient doesn't need any treatment. Right. So for quick conclusions of the paper, we present the joint multimodal deep learning framework that provides improved cardiac LMA detection accuracy from routinely acquired Cine, and CMR images. And we have experimental results shows that our work substantially outperform current approaches, including a promising convergence of accessibility and accuracy in the analysis of CMR stream imaging. And finally, we would focus on further to improve the model accuracy to measure dense performance, because if you look at statistics, there's still a kind of gap. And finally, throughout values model generalizability as patient data become more available to do more data collection and data cleaning and everything. And hopefully, in the future, we can publish these data sets. Yeah, that's all. Thank you.
Thank you very much. The paper is now open for questions. Any questions from the audience? Okay, please go ahead. Mike,
it's fine. Recently,
it's hard for people to
okay.
So, meanwhile, as they come, I'll ask you a quick question. Have you tried doing this in some other set from another hospital to make sure, if you use deep learning or to use on some data from another hospital, external validation?
Yeah, it's kind of, because the DENSE, as I mentioned, is super expensive, right? So for our current research, we only include data from UVA, but we are doing really collecting the DENSE data from multiple institutions, and hopefully then we'll have recently in the near next month or next 2 months, we'll publish a paper that use data from 6 or 7 institutions.
Okay, thank you. Go ahead.
Oh, actually, I have follow-up questions. So recently, doctors has been very concerned about the interpretability of the models. So as a computer science, I believe your method has strong interpretability. But could you share what feedback that the doctor you collaborate with has been giving regarding the interpretability of your method?
Yeah, because that's a great question. So basically, because we break up the model into separate pieces, right? So theoretically, you can just do it end to end. You input Cine images and output the 2S, right? You can. Before then, the interpretability is a big problem, because nobody knows what happened to the dramatic domain transfer images to 2S. So it's hard. And because we separate things, so we have something in the middle that's registration, that's totally understandable, and we have stream. And stream rejection, totally understandable. And from stream to 2S is Also, because visually you see that overlap, it visually makes sense. So we don't have many questions for that. Yeah.
Okay, thank you.
Okay. Thank you very much. And I think is this a quick question because we have to move on here? Quick question. But we have little time, so 30 seconds. Huh?
Okay, so my question is, so that you and try to avoid doing dense imaging and get the same result, but it's your training data, I guess these are matched between Cine and dense, right?
Right. So we.
So
Yeah.
I mean, first of all, do you use the circumferential strain or which?
Circumferential strain.
Circumferential. So I mean, it's very patient dependent. I mean, how can you, if you train, so to extract from Cine data strain in one subject, and if you're training the trainer that cannot really foreseeably cover all possible diseases.
Yeah, that's why we particularly focus on the LMA, right? That for all diseases, that's a kind of a broader view. So
you can't make that general statement. I mean, I guess that's what I'm getting at. Maybe in a particular area that could work, but one cannot really say that this will work, on a plethora of diseases.
Yeah, I think that's actually that's true for every motion tracking method, right? How do you guarantee motion tracking method is good for every disease? So so that's why we want to collect more data from more institutions that has more diverse patients and actually include healthy volunteers to validate the generalizability of the model. But yeah, that's totally a reasonable question.
You collect data from base to apex?
Currently, so Ninja's work is all from University of Virginia.
No, I'm asking if you cover the base all the way to apex of the heart?
The raw data has, but we do not use the very basal and very anti-test because the motion is very, it's hard to detect motion from that.
Okay, thank you.
Thank you very much. Okay, let's move on to the last paper of the session on physics-informed graph neural network for super resolution of 4D flow MRI. Dr. Kazemic.